We're live.
All right. So hi everybody, and thanks for joining us. And this is going to be our first hangout. If it works well, we might have more. And it's a chance to take advantage of this great opportunity Coursera gives us of meeting people who are interested in what we're doing from all over the world. And in past iterations of the course, we've had great fun. And so thanks to everybody who's joined, and hey to everybody who's watching this, who's not on the broadcast. The way we do this is typically we'll just go around and have everybody introduce themselves, say something about who they are and where they're from, and something they want to say about the class or ask a question, and that'll get us started with a conversation, and then we'll just see where it goes from there. And we'll go until we run out of things to say, or more likely run out of time. And if things quiet down, then there's a whole list of questions that people have asked who are not on air, and we can address those as they come up. So to start with, I think we'll just go around and have everybody who is on the broadcast say hi, where they're from, and either make a comment or ask a question or somehow launch the beginning of a discussion in the class. And then we'll see where we go from there. So Justin, do you want to call on people? Because I don't see their names, so I'd have to guess.
Nasser, do you want to start?
Sure. Okay, so my name is Nasser. I'm from Saudi Arabia. But currently, I live in Canada for studying. I was thinking, I do have a question, and if I do understand orbiting correctly, a celestial object has to move in a certain velocity to be pulled down by the gravity and to orbit the planet or whatever it is. So my question is it possible for Earth to have a second moon, or for the sun to have other things orbiting it, and so on?
So that's a very cool question, and the answer is yes, it is possible for Earth to have a second moon, as we will see in the week after the break, in fact. Depending on how you define it, you could say that Earth does have a second moon. So there is another object that is in orbit roughly around Earth, as we'll see, not in exactly the same way that our moon is, that the one we know is, but we do have a sort of second moon. And in principle, there can be lots of other objects in orbit around the sun. We think that there actually are many hundreds of thousands of objects in orbit around the sun that we have not yet found. Obviously not in orbits near where we are, or we would have noticed them. We have a pretty good catalog of the asteroids, say, in low orbits around the sun, but in higher orbits, out past Neptune's orbit, we think there are hundreds of thousands of as yet undiscovered things in orbit around the sun. So the solar system actually is a lot richer than 8 planets and a few moons. And we'll talk about where we think all that came from, and that'll be part of what we do when we talk about the solar system. So yeah, there's a lot. We think there's a lot of stuff out there. Thank you.
Great, thank you, Nasser. Matthias, you want to introduce yourself? You'll need to.
Okay. My name is Matías Bani. I'm from Argentina. I like a lot astronomy. I am electronical engineer, and this is a hobby for me. Understand?
Yeah.
Okay. It's very nice. I take this intro astro last year. But I haven't a lot of time for study this, so I hope this year have more time for this. Okay.
Yeah.
Thank you.
All right. Thank you. Yeah. I guess this is as good a time as any to point this out. Some people have been suggesting that this class is a little bit intense, and I think that's a very fair statement. It turns out that there's a lot of really cool stuff to learn about astronomy and about physics in the context of astronomy and what things are made of. And we made the best decisions we could about what to put in or out. But you end up with a lot of things that I think are worth learning and I think are possible to do in the context of the class. And it is definitely true that for many people, getting everything that you can possibly get out of this class takes more time than we have. And some people, it's not uncommon for people to resolve that the way Matthias has suggested, by doing it once and then coming back and doing it again. And at the moment, the class for this year is almost identically a carbon copy of what happened last year. And so, in some sense, I find it almost gratifying that people are willing to try to do it again, even though they know they're going to hear essentially the same lectures. So I guess that means that the universe is an interesting thing. And so this is, I guess what Matthias is suggesting is for other people who are doing it for the first time and feel a bit overwhelmed, you're in pretty good company. The universe is overwhelming. And it just takes a lot of work to... I don't know a shortcut to getting to know this. So if you find that there's more to do than you have time to do, you're in very good company. Certainly includes me. So thanks for that comment, Matthias.
No, just to say that yes, just to say that the homework are quite difficult because I hardly understand the way the ecliptic and all that stuff run. And you say first take the exercise. Imagine the Earth is not turning the same way but back way. I hardly understand how it works on the right way.
So that is definitely something that is characteristic, I think, of this class, and that's not a coincidence. That's by design. That was the idea. And now the real question, the exciting question is, after you did the exercise, did you find that you had a better understanding of what is actually happening because you had to imagine how it would be if things were backwards? So did that work, which was the idea?
Not yet.
Touché, Jacques. I don't know what to say about that. But that's the idea. The idea, of course, is not that we're really interested in Earths that rotate backwards, but that by thinking about what would happen if the Earth, why do we want to know what would happen if the Earth rotated backwards? Well, because if we really understand that, then we will have understood what the direction of rotation is determining, and therefore we will have figured out why it is or how it is that what we see is the way we see it. And that first week is very challenging. The math is never beyond adding and subtracting, really, but the three-dimensional geometry of figuring out what you would see if you happened to live on a planet that was spinning and orbiting and tilting and wobbling, that's hard. I mean, it's not a mode of thinking that we get to exercise a lot, because luckily in our life, we're not spinning it other than once a day, and we're spinning very gradually. And in some sense, one way to solve the problem is to run a lot of mathematics through it, throw trigonometry at it, and you can do a calculation, which is what our planetarium software does, and that gives you the right answer. But I think it's more interesting in some way to do it without the trigonometry so that you develop an intuition. So you can imagine, as you look at the stars rising and setting, you can, in your head, imagine yourself on a round Earth that is spinning and see how that is influencing what's going on. And that gives you a sort of feeling of where you are in the world and what is going on. So that's kind of what that first week is for.
Understood, yes.
But it's tough. It's
yeah,
always
very challenging, yes. Mm-hmm.
Yes. Hopefully it'll be worth it. That's the plan. All right.
Hi, I'm Arun Ram. I'm from Bangalore.
And ask a question or give a comment about the class?
Yeah, I did the course in 2012. and I was not able to go past, in fact, the third week or fourth week. This was the first course that I got stumped and failed, because I did a few other courses in Coursera, which I successfully completed. So I came back this year after a 2-year break back to the course to complete. But still I am in the second lecture. I am not even have gone into the third week actually. So though I am taking it at my own pace, because I found that the content was a little bit heavy. Means that's what I found in 2012, and that's still valid. It is intense. And Doctor, I have a question to ask. Recently, there was news about landing object on comet, which was never attempted before. Why was we had means the human as a race had sent uh, objects to moon, objects to Mars successfully 2 times, and things like this. But why sending an object to comet was little more difficult, and why it took so much of time, maybe in 21st century?
That's a very good question, and it has an interesting answer. So we have had spacecraft before that went out to visit comets, made close approaches to comets, collected, in fact, material from the atmosphere of a comet, and brought it back to Earth. We've done all of that. Took close-up pictures of comets, and we've learned many surprising things every time we've done that. What was new this time is that they actually landed, and therefore could do close chemical inspection studies of the comet and drill into it down a little bit below the surface. The reason it's very difficult to land on a comet is because comets are so little. What this means is that basically on this comet, if you recall, when the spacecraft landed, actually, the calculations or the trajectory was a tiny bit off, and the thing bounced. It bounced off of the surface and bounced to an altitude of about 1 mile, and landed back on the comet. Now, if you throw something on Earth about 1 mile up, well, it'll land back on Earth. That's not a big problem. It'll land in a big crash. Here, the gravity is so much weaker because the object is less massive that this jump up 1 mile and down lasted, what was it, 25 minutes? So the craft, basically, it's because the gravitational field is so weak, you have to very, very delicately tune the way that you approach the planet or the comet so that you don't bounce off back into space. You are very weakly bound gravitationally to the object. If you just crash into it, then whereas on Earth, if you crash into it, you will fall under the force of gravity and be smashed, and the problem is slowing yourself down. Here, the problem is that you will just bounce off because the gravitational field is so weak. So landing on a comet is a very delicate engineering feat. It's not a scientific question. It's a question of engineering, and this is why it took until this year for them to successfully do it, and this is why it was such an awesome feat, and why it was so impressive that they managed to slow down their relative velocity so much that they managed to control landing that eventually stayed on the comet. That was the challenge.
Back to landing. So it was not like bounce multiple times and then getting into landing.
Sorry?
No, it was just one bounce and it got into landing. So it was maneuvered to land into on the second instance.
Yeah,
so,
but
okay. But doing that itself was a great engineering feat. Okay.
Yeah, that I think was the challenge. Exactly.
Okay. Thank you, Doctor, for the explanation.
Thank you. Thanks for the comment.
Bartek, do you want to unmute yourself and introduce yourself and ask a question or comment?
Hello there, my name is Bartek. Originally I'm from Poland, but 4 years ago I came to the UK to study languages linguistics at the University of York. And I completed a few Coursera courses before, most of them humanities courses. And then I joined this Introduction to Astronomy course. From what I gathered, I thought it would be way less challenging and a bit more humanity stuff course than it actually is. So this is why I wanted to ask this question about the methodology of the course. Currently, I'm doing homework from week 2, which is taking me literally hours and hours, as it's quite complicated for me as a person who has very little background in maths. So I just wanted to ask, how did you come up with this idea of organizing such an online course with, first of all, these video lectures and then the application of all these problems in the homework section?
So, well, I mean, there are two separate questions, I guess. There. One is why did I come up? How did I come up with the idea of teaching this course? And there's a long history to this, but I've been teaching a course very similar to this on campus at Duke since 2002, on and off. And my approach to teaching has, of course, evolved as I was doing this. But the fundamental philosophy is one that I've held to for a long time, which is there was some thread about astronomy for poets. And I didn't jump in there, but I don't like that terminology. There's sort of a common term on American campuses about rocks for jocks and astro for poets, which is sort of the scientists feeling very good about themselves and sort of implying that poets can't really do what we do because we're better. And I think that's I have a lot of appreciation for poetry, and I'm very impressed by poets. And happily, they don't teach English for scientists or English for nerds. And so the idea of the class was to see, and where it came up, is to see how much of what I think is the really, really exciting aspect of astronomy, which is not, to me, a sort of list of what is out there and where it is and what we call it and what the names and what the words are. But to me, the really exciting thing about astronomy is that while it's very hard to do, we've managed to know a whole lot about what these little dots of light are that we see out there. And we can really look out at them and with confidence say, this is a star whose mass is 153 times the mass of the sun approximately, and whose surface temperature is this, and his chemical composition is this. And this is how that star works. And this is what is going to happen to that star in the future. In 10 billion years, that's what's going to happen. This is amazing. And to me, it's a triumph of human endeavor. And I think it makes for a very exciting story. And it has the benefit, I think, that it is possible, if you put a lot of time and work into it, to actually be able to, at some level, understand what it is that it takes for people to confidently say that star is 138 times as massive as the sun. And I think that that's very exciting. And I think that it helps to get an appreciation not only for what's in the sky, but in general for the kind of effort and thinking and combining and putting together of lots of the work and observations of many people that goes into making scientific predictions. And that at the same time, you feel more at home in the universe is a pleasant benefit. So this was kind of why I set the course up. And it feels to me as though the fact that you're struggling with the homework, the fact that you actually are able at the end of the day to take the information and make something new of it in a strictly scientific way. You're able to make a calculation, make a prediction about, the properties of this putative planet Nursat, and tell me something about it just from data. Well, of course, you're not working at NASA precision. You understand that there are subtle effects you're ignoring, but you're getting the main point, and you can do it. And I find that that's very exciting, and I think that that's why this is worthwhile to me, at least. And I hope that other people agree with me, I guess, to some extent. So that's the point of this class. Really.
What does it mean, NERSAT?
What does it mean? It's just an invention. I have to give it a name. And so it's a fake planet that we made up.
So maybe we'll discover one day.
Maybe, if it's ever found. in some mirror universe. Maybe it exists. Does that answer your question, Bartek?
Yeah, it does. Thanks a lot. After 3 weeks, I still find the course really interesting. So I'm still here joining Google Hangout, which is, I think, a very good sign for a poet, let's say.
Well, like I said, I don't like the term for poets because it sort of pretends that we're dumbing things down. We're not very technical. We don't do the subtle details, mostly because I don't know them. I'm not an astronomer or an astrophysicist. But also because I think they cloud, sometimes they obscure the point. I think the essential point we can all share, and I think that's a glorious thing to do, and I'm glad that you're sticking with it. And I think that having 3 weeks and multiple attempts to play with these homeworks is hopefully going to be helpful.
Thanks a lot.
You get out of it what you can. Cool. I hope you enjoy it.
Augustine, do you want to unmute yourself and introduce yourself?
Hi, my name is Agustin. I'm 56. I studied astronomy at 30 years ago. I am trying to regain knowledge and be in telecom business for the rest of my life. So I am really appreciating your course. So I thank you very much for the opportunity to participate. And I'm very interested to know if the course, or in your experience, the normal people can contribute to astronomy in these days. My question is, there is so much, this a huge amount of information on the network about telescopes that provide free images to anyone. And so from when I was living in 35 years ago, astronomy was the lack of information. Today there is abundance of information. What can we do with all the formulas you give us in homework, in practical words? Probably we can contribute. This is my question.
That is a glorious question, and I love it. And there are many reasons why, despite the fact that it's not my technical specialty, I love astronomy. And what you mentioned is one of them. Astronomy is one of the few fields of science, certainly of physics, in which, at this point in time, what are often called citizen scientists, so people who are not professional astronomers, are actually making real contributions and new discoveries all the time. And there are many endeavors, as you suggest. One of the points, Agustin, is that astronomers are collecting huge amounts of data, more than they are able to usefully process. They automate what they can, but there is an element, a room always for humans' intuition to look at data. And there are people involved in many, many fields of astronomy where sort of academic professionals, I guess, are making valuable contributions. And this ranges, and we'll mention some of them as we go along, but this ranges from the observations of variable stars. Again, there is a database of the properties of variable stars, most of which has been and is being contributed by amateur astronomers. There are people who these days with consumer-level amateur astronomical equipment are of the somewhat high end, are making their own observations of exoplanets, planets about other stars. And for those of us without access or the time or the energy or the wherewithal to get that equipment, there are many organizations that put out into the public data collected by various observatories and ask people to help analyzing it. And this ranges from Galaxy Zoo, where they train you to classify galaxies, and then once you're trained, they show you images of galaxies and ask you to classify them to help with a better understanding of the populations of galaxies, and all the way to the Kepler mission, which makes its data public and allows you to basically look at light curves and try to make to identify potential exoplanets. And the Kepler mission telescope, of course, is now no longer operative, and so what you discover may have to wait until it's verified. But at least one former student in the class's first iteration was part of that project and was eventually the co-author on a paper describing the discovery of a system of exoplanets. And he claimed that at least some of the stuff that he did in this class helped him understand what it was he was doing. At the end of the day, he was looking at light curves and identifying dips, but he could follow some of the calculations that were involved because they were rather similar to stuff that we had done there. So more, I'd say this class will give you context, and then various astrophysics projects will train you in the details of what they can offer citizen scientists to look at. I guess SETI is another project that is very interested in citizen science. There are a whole host of them, and if you look up Google ways to get do citizen science and astronomy, you will find there are lots of opportunities, and we can all make contributions to this field. And that's very exciting. Again, astronomy is a field in which there are, if you notice, there are headlines about discoveries in medicine once in a while, and headlines about discoveries in biology once in a while, and in earth sciences. But there are more headlines about discovery in astronomy, I find, than almost any other field of science. And it's not because there are more discoveries made, but because when there's a new discovery in biochemistry, then typically explaining what it means requires, intense background. But when someone discovers, a new planet that orbits its star in an interesting way, we can all understand what that means. So there are discoveries that are comprehensible to everybody, and that's another fascinating aspect of astronomy. So it's a special science. That's why we do it. Thank you. We have more people who haven't spoken, I think.
Do you want to unmute yourself and introduce yourself?
I don't think we heard when you said the name. Your audio cut.
Sorry, Johannes?
Are you talking to me?
Yeah.
Can you hear me?
Yes,
All
sir.
right.
I apologize about that.
Hello, everyone. Hi, everyone. My name is Ioannis. I'm from Athens, Greece. And I've studied automotive engineering, so I have a background in maths and physics. But I'm also interested as a hobby about astronomy. I was very happy to see that you're using Athens as your example in your first lectures. Was very proud for me. And I'm sending my question in if I wasn't able to participate here, so I'll repeat it. It's how can we practice our knowledge we have gained from this course? And the second question is how can we enrich our knowledge after this course?
So practicing your knowledge, well, there's a lot of knowledge, and how you want to practice it will sort of depend on which part of it you find most fascinating and what you want to do. And some of the people involved in this class are amateur astronomers, and they like to observe. And so the idea in this class is that you'll be able to make some connections between what you know and what it is that you're seeing. Some people, like Augustine was mentioned, are interested in joining the endeavor and sort of making contributions to astronomy. And some of the people who've taken the class have done that, and some of the people who are involved in the class now are actually people who are doing this. So there are many ways to use this knowledge. It depends what you want to do and which part of the knowledge excites you most. If you want to pursue it further, then indeed, I think that this class, despite the fact that it is intense and takes you through calculations, it is really an introduction. It's a list, sort of a vista of what the things are that people are doing, or that people have done in astronomy, and what could be interesting. And if one or more of the topics fascinates you, then there are, first of all, more advanced and more focused online classes, if you want to pursue it in this kind of a Coursera or whatever edX type context. Then there are courses in stellar astrophysics and galaxies and cosmology, and various ways to sort of follow up parts of the class. it will be very difficult if someone tried to construct a more advanced version of a class as comprehensive as this. It would be a 2-year class, and nobody has the energy or the time to survive that. So it tends to be, once you want to specialize, it tends to be broken up, and it tends to require background, because we get away with saying things about the way stars work. If you really want to do it, then you have to follow the details of differential equation solving and quantum mechanics and thermodynamics and all kinds of details that go into the way a star actually works and into the models. So we skim the surface and say what's pretty and what's interesting and try to extract what we can about the essentials. But then to really understand it, as an engineer, you're well aware that everybody knows that a car works because the engine turns the wheels. But if you really want to make it work, then all kinds of details become important. And the same is true in science. We are skimpy on the details here. So there are lots of places and lots of ways to go, and I think everybody will do it in the way that, depending on what their actual interests are.
All right, thank you.
Thank you.
Thanks, Johannes. And Demetrius?
Yeah. A nice picture.
Yes.
Yeah, I'm here. Can you hear me?
Yes, sir.
Okay. I'm Demetrius, and I live here in Thessaloniki, Greece, and I'm a first-year student in the physics department. I've been involved in astronomy 3 years ago. It's like a hobby, I have it, and I am mostly involved in observational astronomy. My question is now, are there white holes or this kind of matter like black holes that, like black holes, we know that they suck light, for example, and all the matter due to the gravitational field. Are there white holes? Because I've read some articles indicating that there exist these things. Can you answer that?
Well, I can't actually give a full answer to that question. Not because I'm avoiding it, but because I don't think we know. So white holes are hypothetical objects which are sort of like a time-reversed version of a black hole. We'll talk quite a bit about black holes in the class. And one of the exciting properties of a black hole is that nothing gets out of it. Whatever is inside some part of space that we call the black hole, and we'll see that that's not exactly accurate, but that's how it appears. There's a part of space that we call the black hole, and whatever is in there will never get out. You can imagine a thing that works in reverse, which is a part of space such that things can only come out of it and nothing comes in. And this crazy-sounding idea has its origins or comes about, becomes realized, when you mathematically solve the equations of general relativity, and you take the neighborhood of a black hole and you sort of extend the solution past where we know the star is. Now, we know that
So it's
typically
like a mathematical model.
this is a mathematical abstraction, because in real life, and we will discuss it, when we form a black hole, typically the part of, I should be careful here, of space-time, where you go through to extend the solution to discover a white hole, well, right in between you and that part is something that collapsed, the star itself, the stuff that made the black hole. And so the solution that you're extending, the vacuum solution, is not actually valid all the way out to where you're finding a white hole as part of its property. So such things could exist. They are, in the sense that they are solutions to Einstein's equation. We have not seen evidence of them, unlike black holes. And perhaps more to the point, unlike black holes, we have not, so for black holes, even before they were discovered, there was, right after Schwarzschild found the solution to Einstein's equation, it was clear that you could imagine a dynamical process, about which we know more and are learning more now, wherein some objects that we know now to exist in the universe, say a dead star, could collapse to form a black hole. So you could start with conditions that we know exist, and the equations, including matter, would lead to a black hole. We do not understand solutions that, starting from the conditions that we're familiar with, would lead to white holes. They violate all kinds of inequalities. And so we have less reason to believe that white holes exist than that black holes do. But we can't absolutely rule them out, I guess, is where I come down. They're mathematically possible. They're probably, my guess is that they don't exist in our universe.
Okay, thank you. And I have one more question. How can I, for example, take an astrophotograph, and how can I extract data from it? Like, what elements are there, and like the spectrum data? I know.
So I'll make two kinds of an answer to this. The first is that you're asking the wrong guy. Even in the context of this class, there are, and I wanted to this gives me a chance to say something else I wanted to say. Even in the context of this class, there are many people who know a lot more about the answer to that question than do I. Roughly, when you say an astrophotograph, a lot depends on how you took the photograph. And so if you took, say, a collection of photographs through 3 filters, or alternatively, color digital photograph, which is essentially the same thing, a collection of 3 filtered photographs, then information like line spectra is not going to be visible in that, obviously, because you've now got 3 numbers and you can't extract line spectra. You can extract for various of the objects in your picture roughly their color. So you can do lots of things with a 3-color photographs. We'll talk about how you can take a picture of a star cluster and extract its Hertzsprung-Grosso diagram, for example, just out of these 3 filtered photographs. The technology, the technical aspects of processing, I can give you the rough picture, but the details, there are people who know more than I do here, and I invite them to answer you. If you post this on the forums, then you'll get a better answer than you would from me. If you actually want line spectra, if you want to do chemistry with your picture, then you need to put a diffraction grating and actually take a line spectrum. So you would take a spectrum of one star rather than, or of one object, rather than trying to take an image. Simultaneously, imaging and taking a detailed spectrum is very difficult, right? Because the grating smears the image. So you typically take the spectrum of a particular object. And in more generality, I wanted to say that there are many great things about this class, none of which the ones I'm talking about have to do with the lectures I recorded. One of the great things about this class is that we have, 20-some thousand people, all of whom are here because they wanted to, so all of whom have some real interest in astronomy. Each of whom knows different things, right? So some of us are humanities people, and some of us are technical scientists. Some of us are engineers. A lot of us are amateur astronomers. And one of the awesome things about this class is that if you post a question to the forum, such as, hey, I want to take astrophotographs and extract spectral data from it, how do I do that? There are people, and some of them are, there are some people in this class that I know, I just don't want to name them because I don't want to call them out and make them feel obligated, who can give you an answer because they do this all the time and are very good at it. And so I want to encourage you guys to use the forums to some extent. The obvious use of the forums is it's like raising your hand in class, right? You ask a question, a CTA answers, you have a conversation, you can finish the homework. That's a very good use of the forums, but it can go much better, much farther. You can post questions and ask the class to answer, and you can get answers from a huge collection of people, some of whom know. And even when your question is, how do I solve homework, 2A part 6, in some sense it'll be more useful if you collect a group of your colleagues who are working through the same kind of thing, and you work through it together rather than get an answer to some confusion. I find that that's a really constructive way that these classes work. So one of the great powers of this way of learning is that we can harness 20,000 of us doing it together. and I encourage you guys to take advantage of it and to contribute, I guess. That makes it cool. So thanks for giving me an opportunity to give a speech.
Thank you very much.
Thank you.
Great. So, Ronan, right now we have quite a few questions from other students who have posted them, and I thought I have a few of those come up here.
Okay.
I'm going to start with one from Paula, and hopefully you'll be able to see this here too. But if the orbit of the planets are mostly ellipses, doesn't that mean that in any given time there will be the possibility for two planets to collide with each other? It's Paula's question.
So thanks, Paula. And indeed, the orbits of the planets are almost exactly elliptical. They deviate slightly from ellipses due to the perturbations of one planet by other planets and whatever. But they're very closely approximated by ellipses. Now, in general, if you put a bunch of ellipses around a star, you have to remember that planets are, even if you're talking about Jupiter, a couple of 100,000 kilometers across. And the distances at which the planets orbit around the sun are, tens of astronomical units, so billions of kilometers. And there's a lot of space around the sun. Remember, distances get cubed to make volume. There's a lot of space around the sun, and it's almost completely empty. So with a small number, 8, 10, whatever planets, the probabilities of the two of these planets, even having their orbits intersect is unlikely. Having their orbits intersect and having both planets be at the same place at the same time, extremely unlikely, basically because space is so empty. And most points of space are not on the orbit of any planet. And at any given time, most of the points on the orbit of a planet don't have a planet in them because a planet is somewhere else. And so collisions between planets in the current configuration of the solar system are very unlikely. This changes when you have lots of objects. And in particular, when you have lots of objects, then you increase the probability that some pair of them will come close enough for their mutual gravitational attraction to deflect them from the elliptical paths they were on around the sun and to get them, say, orbiting each other or even colliding with each other. What's an example of this? Well, when you think beyond planets and you include all kinds of asteroids and comets and stuff that is following very eccentric orbits around the sun and that is smaller, then indeed we know that there are ongoing collisions between various stuff and, say, the Earth or the Moon that make craters on the Moon and that cause meteor showers here on Earth. So obviously, if you go down to little stuff of which there are many billions of little pieces flying around, then you do get collisions. But if you're populating the space around the sun with on the order of 10 or 100 very small objects, small relative to the size of the system, then they're very unlikely to collide. In the past, I should say, there were more larger, or not quite as large as today's planets, but in the early days of the solar system, before the formations of the current planets, there were many medium-sized objects, and collisions were, we believe, far more common. And we'll talk about that in the next week of the class when we come back from our break. So details of this we'll answer in more detail how this question could be answered, but it's a very good question, and in fact a very interesting one. Thank you.
I have a remark on that question, if it's possible.
Shoot.
Have you watched the movie Armageddon, where they tried to shoot up a comet from Earth so it wouldn't hit Earth? I'm wondering if that's would we actually do it, like see a comet that's coming towards Earth, and then we'll shoot it, or like just to change its direction. Does that actually happen? And
so it certainly never happened. Excuse me. I'm sorry. It certainly never happened in the past. There are resources, and I'll give you a link in next week's with the fifth week's lectures, but you can find it yourself. There are many hundreds of thousands of objects that we know of that are on orbits which, if perturbed, could bring them near Earth. We suspect there are many more of which we do not know that could be deflected into orbits that would bring them near Earth. And there are people who are seriously considering, and as you computed in second week's homework, the effects of a collision, should it occur, can be somewhat dramatic. And we don't have to hypothesize that. It's good that we could do the calculation. We also have experimental evidence. It has happened, and we can see what happened in the past. And so, so there are people who are thinking very hard about what could we do to prevent such a collision. And the answer, it seems, is that, well, blowing up a comet before it reaches Earth is kind of a bad idea, because you haven't really changed the trajectory of the center of mass of the thing. It's still, you can't change that. All you have is you've converted one big object into a lot of small objects. That's not clear that you've gained anything. The total energy of the impact is not much change. It's now more broadly distributed in space and time. That could, it's a question of details. What one could imagine doing is sort of setting off an asymmetric explosion, trying to deflect an object. You don't need to deflect it much if you do this when it's still very far or very far in time from Earth, so that a small change in its initial conditions, if adjusted correctly, over time, if you get it a few years before it gets here, can accumulate to it missing Earth, by the distance to the moon, rather than crashing into us. Great, no problem. So it is probably technically feasible to take a large object and change its trajectory from near Earth or Earth colliding to safe, if you catch it early enough. And the question is, how much resources is it worth investing in developing the technology to A, do this, and B, to manage to detect things early? And this comes down to a computation of, what is the probability per century of such an event happening, and it gets in details of understanding the composition of the solar system. And so there are valid questions that people are addressing, how this competes with fighting Ebola. And it's a question of distribution of resources that requires, again, knowledge of the details. That's what it comes down to.
Thank you.
Sure.
Sorry, I've got a more general question about astronomy. What is really interesting in astronomy is that you have an open book, and you don't do specific experiments. You have everything, and you discovered it. But what is a bit astounding is that, for example, when you imagine Ptolemy's model, it was working fine until we discover something wrong about Kepler. And from century to century, we go and refine the theory. But what I'm afraid of is that, in fact, is there a way to really touch the reality and not only having models? How can we appreciate reality? And maybe all things you are talking about are only models. For example, black hole or things like that. You say we never really observe them, but there are models of what could be done. And how can we reach the true reality, in fact? That's the main question I have.
Well, that is a question that can be addressed at many levels, I guess. And I'm certainly not qualified to sort of give a long, good discourse on the the relation between epistemology and ontology, and what does it even mean to say reality. So I'm gonna duck down to my own intellectual level, and say that for the purposes of this conversation, what I'm going to take as reality is, if you have a model, and the model suggests that these measurements will lead to those answers, well, then I'm going to take that model as being reality. So I have a very difficult time, making a rigorous, logical argument free of assumptions that you, Jacques, are actually a person talking to me and not some simulation in my computer.
Yes.
But on the other hand, the assumption that you're a real person and that you react like a person seems to work very well, and it describes all the things I know about the world. So, you know, I don't want to argue with Descartes one way or the other. I'm going to just accept that it's a very good model to assume that you're out there and you're a real person and the universe is real, and therefore, by the same extension, that if someone solves the equations of the physical theories that we can test right here on Earth about the properties of gases and the properties of metals and the properties of atoms and the gravitational effects or whatever, and then extrapolates them to some other regime and says, well, if there were an object described by these equations as a black hole, then I would expect the following phenomena to take place around it, some of which are observable. And then we go and make these observations, and we find these phenomena happening together. This along with that, this spectral property along with that velocity distribution, along with this chemistry, along with this ionization state, along with this temperature. Okay, then the model is working very well. And if someone someday comes along with a measurement that doesn't fit in, then as you say, we refine the model. It's important to note that very few times is the refinement of the model as extreme, if you want to think about it that way, as the Copernican revolution.
Mhm.
We don't overthrow a model. To some extent, the Copernican revolution, depending exactly on what you take the heliocentric model to mean, or what you take the Earth-centric model to mean, in some sense it might have been a revolution, really throwing away the old model and replacing it with the new. If you just talk about the mathematical description of the apparent motions of the planets and on the celestial sphere, then it was just a refinement. It was just a small change. But it came from a deep underlying change in the model. So that has happened, that kind of deep underlying change has happened a countable 10, 5, depending how carefully you want to count, number of times. So relativity is such a change. Quantum mechanics is such a change. But quantum mechanics only refined the predictions of the kind of Newtonian mechanics that we learned last week. It did not overthrow them. Did not revolutionarily say that, oh, everything you knew about billiard balls was wrong. It just said there were tiny details that you didn't observe when you looked at billiard balls. So in that sense, Newtonian physics is still very much a part of the model, and I hope that our mechanical engineer, our automotive engineer friends, when they design cars, are not doing relativistic calculations or quantum calculations. Newtonian physics works very well. Describes everything you need to build a car. And so we don't, and so in that sense, it's as much a part of reality as anything else. And you ask this question in astronomy, I always like to ask people, do they believe in electrons? And I am almost confident that electrons exist in the sense that their models we mathematically compute based on their existence have very good agreement with reality, and my computer works fine. But I've never seen an electron, I've never tasted an electron, and I don't think I ever will. So,
Okay. Thank you.
Thank
you very much.
That's all we have.
So, Ronan, we're getting close to the end of our time here, and we had a question from Ferdinando that I thought would be a good way to close up here. And his question is, what's your favorite thing about astronomy?
Ooh, wow. That's a tough one to answer. There are a lot of things I like about astronomy. I guess I would start with the fact that as a physicist, as a person who really likes the idea of approaching and understanding the universe by writing models and making calculations and comparing them to measurement, who finds that really exciting, astronomy is a wonderful application of physics because basically it unifies everything that we've ever discovered about the nature of the universe, about physics, has an application, is important in astronomy. It sort of brings it all together. And it brings it together under all kinds of extreme circumstances that highlight aspects of interesting physics that are very hard to simulate, to make as relevant by doing experiments on Earth. And so on the one hand, it involves an application or a use laboratory for all known physics. And on the other hand, as I said before, there are aspects of it that even a layman like me, who's not an astrophysicist, who knows nothing about real stellar modeling, can appreciate and understand and enjoy, and can share with lots of people. And it's sort of this simultaneously being very deep and very thorough and very systematic, and on the other hand, being right out there. I can walk out, and I do whenever I get a chance, and look up at stars and see meteor showers and take out my little telescope and get a look at the Ring Nebula. And then I can go back and think about what I know about science tells me about what that weird shape that I'm seeing actually is. And I find that collection exciting. And then, you know, for my more humanity-oriented part, I find that the history of the field, the way that people have put together this model of the universe and have refined it and have changed it when needed to be and have come up against the philosophical questions that Jack was asking and answered them in various ways. And the way that this all, because it's so immediate, is intimately connected to our culture and the way we think about, have been thinking about ourselves for thousands of years in various ways through at various civilizations. It's just fascinating. It just puts everything together. It touches almost every aspect of what interests me, even poetry. So it's fun.
May I have a last word about the lectures?
Please.
Actually, I was struggling the first week with the first topic to put everything right in my mind. So, and I work full time, and I feel like I have left a little behind because yesterday I finished studying the second topic, and now we're already in the third. So maybe a week off after week 4, for example, in the middle of the course, just for everyone to catch up, it would be a great idea, I think. Because I work full time, but I still want to conclude the course, you know, in the right way, and the exams and everything. So to me, it's a little bit difficult to find extra time to do the course. So a week off from the course in the middle of the course, it would be great, you know, to catch up. So maybe you should consider this, because maybe other people have difficulties to follow the course.
So Johannes, many people, as you point out, both in the past iterations and in this one, report that it's intense and that they have difficulty finding time. And one of the ways that we have responded to this is precisely what you suggest. We have 2 one-week breaks in the class, one of which you'll be happy to hear is this coming week. And so week 4 is in fact not a week. There will be no new material released in week 4, and we will start the 4th unit in week 5, and so you have time to catch up. And once more in the class, I believe it is the last 3 weeks, the 3rd week before last, is it 8?
Week 9 is a break week as well.
Week 9 also has no new material associated to it, so that there are 2 one-week breaks built into the class, exactly to help people who got busy and need time to catch up. And I should point out there's another virtual break at the end of the class, because after we stop, after the end of the 12th week, we've posted everything we have to say. You still have 3 weeks to complete that last homework set, because we have 3 weeks for every homework set. So, in fact, the class extends over 15 weeks. Does that make sense? And
yeah.
If you want to take the exam, then that will be open during that period. And so you do have options for spreading out when you have a particularly busy week, making more space. It doesn't lessen the total amount, but it does help you spread it out in time.
All right.
And I hope you find it useful.
This is great. This is great. Thanks a lot.
Thank you.
Okay, well, I think we're all out of time here, and I want to thank all of our participants, and especially Ronan for his time to talk today. And I really appreciate all the questions everybody sent in. I will try and put those into the forum so that we can all discuss them. And maybe if Ronan has time, he can respond to some of those as well.
I happily will, but as Justin says, I encourage anybody else who has something to add on any of these questions to jump in, and we'll have a much richer discussion that way. All right, thanks to everybody for joining, and thanks to everybody who's listening, and thank you for joining the class.
Thank you.
That's what makes it
Thank
fun.
you.
Thank you.